Hello, my name is Ryan Bueller. In this video, I'm going to review the maximum height of snow distribution across British Columbia during the winter 2022 season. Start with a little bit of background. This project was originally completed in November 2021 as my final project for the BCIT Advanced GIS Certificate Program. And then just a few days ago, I've pulled in all of the winter 2022 data to update the map for this project. The project area is confined to British Columbia and uses the maximum height of snow data for any station that was readily available. The majority of the data comes from the BC Ministry of Transportation and Infrastructure, Environment Canada, Parks Canada, and the BC River Forecast Centre. And the graph on the bottom just shows an example of the type of data we're using here. I'm going to go through these slides really quickly. There's additional videos available on the tutorial which goes into more detail. So of the three types of snow height data, the first is manual snow height data measured off a stake by a person at a weather plot. The second type of data is automated using a downward facing sensor. One thing to note here is this is error-prone data, so you have to be diligent about removing any errors before you actually take the maximum height of snow data for each year from the data set. And then finally, our old school snow course data. The problem with this is that it's only measured once a month, and we're interested in the maximum for each year, so you're going to miss it with this type of sampling. But the advantage of this is it goes back a long ways, longer than most of the other types of data. And it's typically in mountainous, deep snowpack areas. So there is some usefulness of this data. It's just that it's not sampled very frequently, so you have to remember that. So just to summarize here, BC MOTI electronic data is all automated. I took some liberties here and I combined the older manual height of snow data with the modern automated height of snow data where the plots were in the exact same location. So there's maybe a bit of error introduced here, but I think it's pretty good. And this creates much longer data sets, which is better for statistical analysis. Parks uses manual data up in Rogers Pass. And Environment Canada uses a mixture, and I also took some liberties with Environment Canada, combining their older manual data with their modern automated data where the point was in the same location. And then finally, BC River Forecast Center's snow course data. So the second part of this is to just cover the basic statistical methods. I'm also going to go through this really quickly. You can pause the slides to read it or watch the more detailed video. So the first of the two types of statistical methods I've used to normalize this maximum height of snow data is the annual percentage of average. This is pretty common to see on the BC River Forecast Center maps. If you've looked at these, essentially 100% is the average. Anything below 100% is below average for the year, and anything above 100% is above average. And when you plot this on a map for each station, it looks like this. And we'll go into more detail on the actual tool. The second method is to use extreme value distributions or Gumbel distribution. I'm not going to go into the weeds with this, but basically that plot there shows the distribution for an extreme value type 1 where our extreme event is on the high side. So we're going to use Rogers Pass as an example here, and you can see right away if you look on the left side of the graph, 1972 really stands out here. It's well outside of 2 standard deviations. So the first part of this is covered in Bruce's book, chapter 6, about how to do the non-exceedance probability. And instead of using a ranking method like he describes in his book, what I'm using here is the method of moments. And basically what the methods of moments means is that we're assuming our sample is representative of our population. So it fits the curve on that previous slide. And then what you can do with this is you can calculate your scale parameters B and U from your mean and your standard deviation. So it's very quick calculations once it's all set up in a spreadsheet using this method. So back to Rogers Pass. If you go through the calculations, you get a B of 26 and a U of 184. So taking those numbers and plotting them back into this formula for X for an event, we can calculate the values for any given return period. So in this little table in the bottom left, we've got the 10-year, 30-year, and 100-year, and then we do our calculations for each. And then we can say, based on our data set for Rogers Pass, and this is not updated this year, it's from 2021, our 10-year height of snow at Rogers Pass would be 243, 30-year would be 273, and 100-year value would be 304 centimeters. Again, these are all statistical estimates, and there's lots of places for error to be introduced, so these should be considered ballpark, and this is really all just for educational purposes. But you can see once you've calculated these numbers, you can actually plot them back onto your graph. So you can see, again, the 1972 bar is well above the 100-year height of snow value, estimated height of snow value here. So creates a good visual. You can see a couple other events which have exceeded the 10-year value. This method is common for design purposes. If you wanted to know your 100-year height of snow at some location, you could do it this way. What I've done here that's a little bit different is I've flipped the formula around. So instead of calculating the value for any given return period, I've taken the values for each year and I've calculated the return period for that year. So again, looking at 1972, if you put it into this formula, 319 centimeters ends up being 174-year estimated return period for that given year. And if you looked at 2021, you're seeing a value of 1, just a typical year. So if you do this for every station, you could get a map like this with each station having a return period represented by a bubble. And I'll go into this in more detail on the actual tool. So when you first arrive at the tool, this is the screen you'll be seeing. At the top, there's 5 tabs. Each of the first 4 are tools, and the 5th is a tutorial. You can see I've only updated 2 of these, and I'm only going to cover the 2 in the video here. So this first tool is looking at all the points in BC that were available and using the 2 statistical methods that I just described. But I'm actually going to go at the bottom, there's 3 tabs, 3 different maps. I'm actually going to go to map 3 first. This is the actual height of snow data. And you can see in map 3 legend the distribution here of the different colors. So from less than 50 centimeters to greater than 300 centimeters. The original version of this didn't have this, but I thought it was actually useful to look at the real data. And I also should mention this is the 2022 data. You can quickly click through and see the different years, but you can see that with this tool, this map, a pretty consistent trend of where the deeper snowpack stations are compared to the drier ones. So there may be some use for actually looking at the raw data here. You can see, Rogers Pass stands out as a deeper area. We have some deeper areas around Whistler and the North Coast. But I'm going to go back to map 1 and focus on the normalized data. So what we're looking at here is the percentage of average for 2022. And this is map 1, so you look at the map 1 legend. And the medium-sized yellow circles are 90 to 110%. So that's an average, right? And anything smaller, orange going to small red is below average, and anything into greens and blues is above average. So right at a glance, we can see sort of a distribution of some of the areas that were below average, a few areas standing out that were above average. But we want to dig down a little deeper. As we zoom in, we see the labels appear that show the actual percentage for that station. So right around Revelstoke, we're seeing 98 to 110, some average values. Through the Okanagan, there's a bunch of values in the 70s and 80s. But it's important to note here that we're talking about a bunch of low elevation stations. We have a few high elevation stations, some wet areas, some dry areas. So we're looking at a total mixed bag here. So it's important to think about using some of the filters here. So the first one I'm going to do is I'm going to turn off the snow courses. In the modern era here, we have such good electronic data that we don't necessarily need to look at the snow course data. But I'm just going to show you for an example here. If we go back to, say, 1972, there's not a lot of data. So this is where the snow course data really shines, right? Lots of data going back as far as the 30s with the snow course data, but a lot less other types of data here. So going back to 2022, I'm going to leave the snow courses off and just focus on the higher quality data. Right off the bat, I'm going to show you there's a lot of low elevation stations, right? So if we set our upper bound to about 1,000 meters, now we're looking at valleys, essentially. And we start to see a little bit of a different picture here. We're seeing mostly yellows and greens, and then a bunch of blue circles in places. And then just to flip this around, I'm going to set that back to the highest, and I'll set the lower one to 1,000. Now we're looking at higher elevations. We're seeing a slightly different picture, a lot more oranges through the central Okanagan. Mostly average, maybe slightly above average in the mountainous areas. Another way to look at this is to only look at wet stations. So if we think about the average maximum height of snow we're interested in, we can remove the dry stations. So if we say initially we're only interested in stations where the average max HS is greater than a meter, you can see it reduced the number of points quite a bit. And now we're just looking at our wetter, mostly mountainous stations. We can go even a bit wetter. Seeing similar trends here, pretty average around Whistler, slightly above average in Rogers Pass, maybe as much as 25% above average. Pretty normal through Revelstoke and Micah. This one has been standing out. Paulson Summit saw well above average, 150% of average this year. So it's a bit of an outlier when you're looking at it from a sort of a higher level. Looking at the north, I'm going to reset these. We saw above average on the Salvis on the immediate northwest coast, but as you moved inland, it became more average or below average for the northwest inland. There's one snow course up in White Pass, which was above average. And we saw some above average values in the northeast as well. I'm not going to spend too much time. I just wanted to introduce how to look at this and to highlight the filters because they're so important here for actually narrowing down what you're interested in. I'd be curious, take a look at this and tell me what you think. If you see any errors in data in your local areas, those kind of things, I'd be keen to hear what you think. So now I'm going to go to the second map. This is the new sort of way of looking at this. Using Gumbel extreme value statistics, we can now look at the distribution of extreme events in a similar way here. So switching map legends to map 2 legend, we can see the biggest circles are greater than 300-year estimated return period. The tiny ones are 1 to 3, which is what I would call a typical winter. So we can see a few circles here that are standing out as being statistically significant. Again, Paulson Summit down in the south is showing up as an estimated 46-year return period event. Up in Rogers Pass, Mount Fidelity was showing as a 15-year type of a return period. 13-year down Rogers Pass. I'm going to turn the snow courses back on. One that stood out was the Glacier Snow Course. Again, these are only measured once a month in the winter, so you're likely missing your true maximum value, but this is an 84-year data set, so it is still relevant to a certain extent. The average of this data set's 190, and this winter they measured a maximum of 300 centimeters, which was 158% of average, and gave an estimated return period over 100 years. So once you've kind of tuned your eyes to these circles, you can look at it at a high level and immediately start to pick out trends. We're generally seeing through most of southern BC pretty typical sort of winter, maybe a little bit above average in a few places. One place that stood out to me right away was the Fraser Canyon. All 3 stations picked up larger events, and you can click back and forth. You can see these same 3 here, well above average, 200% of average, double the snowpack. But these are quite dry stations with, your maximum height of snow is 72 this year versus an average of 35. So it's double, but it's not double a huge amount of snow, right? I think there's a lot more variance in the snow courses, so I'd be very wary of the actual values from the snow courses because the calculation is based on the standard deviation. You're likely going to get higher values than are realistic for snow courses using this method. Sorry, this is the map here. Pretty typical values through most of northern BC this year. One last thing before I finish, I'm going to turn the snow courses back on. I'm going to go back to Glacier Snow Course. Like I said, this was really stood out for the interior. So what I'm going to do is I'm going to switch on the top here. I'm going to go to the station info and time series tab. This is going to load the other tool that I've updated for this year. This is intended to look at each station individually, and some of the same sort of filters if you want to reduce the number of points. But what I'm going to do is zoom into Rogers Pass. I'm going to click on the Glacier station. It's going to pop up some additional information, including the estimated 10-year, 30-year, and 100-year for that station, the observed max and min, the average, and number of years in the data, those kind of things, those metadata for each station. But what's important here is at the top of the pop-up, there's a select button. If you click the select button, and it actually selects the point, and it will bring up the time series. So this is showing the 84 years of data, and you can see 2022 300-year value was the maximum observed, just slightly more than 1972. But again, this snow course data introduces a lot of variability, so it's better to look at something manual. Nothing better than Rogers or Mount Fidelity. Select. So here's looking at slightly shorter period, but higher quality data, and you can see here 72 stands out, just shy of 5 meters versus 2022, which was 440. So definitely less of an extreme winter when you look at it, this sort of data set. Thanks for watching. There's a link to the tools below for you to try out. I'd be keen to hear your feedback. If you find any errors, if you have any suggestions for additions, or you want to send me high elevation height of snow data from a ski hill, I'm all ears. Thank you.